Testing. Okay, I lost my voice a few days ago, so if this lecture is to continue, you guys need to keep very quiet today. Otherwise, you won't be able to hear anything. Or if you do not want to sit in the lecture, you may go off. Okay, I'm going to start. Okay, recap of what we did last week. We talked about equipotential lines and surfaces. Basically, they are lines and surfaces where the potential is constant. Then we talked about potential gradient, right? The relationship between the gravitational field strength G and the potential gradient. We say that the gravitational field strength is the negative of the gravitational potential gradient, which is the rate of change of potential with distance. A similar relationship exists for gravitational force and gravitational potential energy. Gravitational force is the negative of the rate of change of gravitational potential energy with distance. Okay, then we look at how we plot graphs of G against R and potential against R. Right, so you need to be able to sketch these graphs yourselves. It could be different combinations, right? It could be two masses that are equal, or left mass bigger than right mass, or the left mass is smaller than the right mass. You need to be able to sketch for all these different combinations of masses. And then finally, we look at how to determine the speed of a body that is orbiting in a circle. So today, we're going to look at how to determine the period of a body that is in orbit. Okay, so here, we have a satellite that's orbiting around Earth. So in order to maintain circular motion about Earth, the satellite needs a centripetal force. Now, what can provide this centripetal force? If you look at the free body diagram of the satellite, there is only one force acting on it. That is the gravitational force that Earth exerts on the satellite. So therefore, the weight of the satellite must be the one that is providing the centripetal force for the satellite to move in circular orbit. Right, so we write down this statement. In equation form, because it's circular motion, we always begin with the same equation. Summation of forces pointing towards the center of the circle equals to mass times centripetal acceleration. In this case, on the left-hand side, there's only one force, which is the gravitational force, okay, gmm over r squared. Acceleration, I will not use mv squared over r, because I'm finding period, so I will use mr omega squared. Here you've got to be careful. On the left-hand side, the r represents the distance between the two masses, right? The distance between the satellite and Earth, that's r. On the right-hand side, the r represents the radius of the circle. In this case, both are the same, so I use the same letter r to denote. That omega, I substitute 2 pi over t, the period of orbit, and end up with this expression. So this particular term is a constant, so I can say that the square of the period is proportional to the cube of the radius of orbit. Right, and this is an important outcome. Right, when different objects orbit around the same body, in this case Earth, if I have many different satellites all orbiting around Earth, right, the square of the period of the orbit for each object is proportional to the cube of the radius of that particular orbit. This is known as Kepler's third law. You don't really need to know this law, right? The result, you can just use if it's an MCQ question, but in the case of a structured question, you cannot quote this law. You got to derive it. You got to derive this expression as you've just done, which is not too difficult, right? Just circular motion concept. So a few things to note. From this relationship, we can see that the period of the object in orbit is independent of the mass of the object. Right? It only depends on the radius of orbit. So two different objects have a different mass, but with the same radius of orbit, right? They are both orbiting about the same source mass, for example, both orbiting around Earth. Right? They will have the same period if their radius of orbit is the same. Doesn't matter what their mass is. Right? In this relationship, t squared proportional to r cubed, you got to derive the expression before you use it in structured questions. In MCQ, of course, if you remember this relationship, you can just use it. And then finally, we look at how to determine the various energies that an orbiting body possesses. Right? Now we have a satellite, right, mass small m, orbiting at a distance r from the center of a planet. Right? This planet has mass big M. The GPE possessed by this satellite, we can just quote, right, this we have learned it. GPE is always negative minus GMM over R. How do we find the KE of the satellite? Right? We use the concept that we just learned. We have already seen this earlier in the lecture. Right? The gravitational force exerted by the planet on the satellite provides the centripetal force which the satellite needs to orbit around the planet. Right? Because it's in circular motion, we equate all the forces acting in the radial direction towards the center of the circle to mass times centripetal acceleration. In this case, there's only one force, that's the gravitational force, are equated to mv squared over r. V squared over r because I want to find the speed, so that I can find the KE half mv squared. Okay, from there, you can determine the expression for the speed of the orbiting body. This you have derived earlier. You need to know how to derive it yourself if you are solving structured questions. Once you have V, you can find the KE. Right, KE is half mv squared. So the V squared, you substitute this expression in, right, you get this expression. So there you have it. This is a KE, expression for KE of a satellite orbiting around a planet. This expression is not to be memorized. For MCQ question, yes, if you can remember, that's good. But for structured, you got to go through the derivation right before you use the expression. So what is the total energy possessed by the satellite? Total energy is just the sum of the GPE and KE. So you add up the two expressions, you get this. Total energy is always negative, as you can see. Right. The numerator, they're all constants, assuming the mass of the satellite doesn't change. So total energy is inversely proportional to the radius of orbit. Again, this expression for total energy, right, you got to derive it before you use in structured questions. Okay, from there you can sketch a graph, right, that shows how the different types of energies vary with distance from an object that's orbiting around another mass. KE is always positive, right? It is inversely proportional to the radius of orbit. GPE, that's the solid line below, is always negative, right? Also varies inversely with the distance r, the radius of orbit. Total energy is always negative as well, right? It varies this way. Now, if you look at the expression for total energy and the expression for total KE, you realize that they are exactly the same, except that total energy has a negative sign in front. Okay, so kinetic energy and total energy, they will be mirror images about the r-axis. This graph is not drawn very well. It doesn't show the mirror image. Okay, so that's the first point to note. If you're asked to sketch the energy diagram for a satellite, when you draw the sketch, you must show that the total energy and the KE, they are more or less mirror images of each other about the r-axis. And you can see from the graph that the further a satellite is from Earth, the greater its total energy is, which means less negative. Total energy is always negative for this satellite, based on the expression we've derived, and the negative sign is part of the magnitude. So the further the satellite is away from Earth, the less negative and therefore greater the total energy. Okay, and this total energy, right, assuming that it's orbiting at a fixed radius, will be constant. Now we learned earlier in escape velocity that if you want to escape from Earth's gravitational field, the total energy possessed by the object must be greater or equal to 0. Because when you reach infinity, your GPE is 0. Your KE must minimally be 0. It can be greater, but it cannot be less. Right? So therefore, the minimum total energy a body must have to go to infinity is 0. But if I look at the expression for the total energy of a satellite, it is always negative. It can never be 0 unless you go to infinity. Right? But here is a finite energy, always negative. What does that tell you? This satellite will never be able to escape from Earth's gravitational field. Okay, so if you are asked, what does the negative sign in this expression for total energy of the satellite tell you? Right, the negative sign represents that the satellite is bound to Earth's gravitational field. Right, it can never escape to infinity. In reality, right, there's air resistance, there's friction in the atmosphere. So the total energy of the satellite will never be constant, right? Because as the satellite orbits, it does work against the frictional forces. It will lose total energy. Okay. So when it loses energy, what happens to its radius of orbit? Right, the total energy must decrease. If I look at this expression for the total energy of the satellite, right, if work is done against frictional forces, the total energy goes down. Right, it must become more negative. Right? A decrease in total energy means that this value must become more negative. The numerator are all constants. To get more negative, there can only be one way. The radius of orbit must get smaller. Right? So as the satellite does work against friction, it loses total energy. The satellite will move into an orbit that has a smaller radius. What happens to the other energies when it moves into this orbit of smaller radius? GPE, if you look at the expression, as R gets smaller, GPE becomes more negative. So the GPE also decreases as the satellite moves into an orbit of smaller radius. As for KE, when R gets smaller, KE becomes bigger. So total KE increases. Okay? So it's not a contradiction. The total energy decreases. So the satellite will move into an orbit of smaller radius, right? And therefore its GPE decreases. But as it goes into an orbit of smaller radius, it actually orbits faster. The KE increases. However, the increase in KE is less than the decrease in GPE. If I look at the two expressions, the decrease in GPE will be twice the increase in KE. Hence, there is still an overall loss in total energy. Okay, so we are done with energies of bodies orbiting. Now we are going to talk about geostationary orbits. Okay, what is meant by a geostationary satellite or geosynchronous satellite? Right, these are satellites with orbits such that the satellite is always positioned over the same geographical spot on Earth. So where we are now, right, if I see a satellite above me, you know that Earth is going to rotate about its own axis. Right, so as I rotate, this satellite will also rotate together with Earth. That is why when I look up into the sky, the satellite always seems to be directly above me. And that is what we mean by a geostationary satellite. A geostationary satellite must fulfill three features. Right? Number one, its period of rotation. Because the satellite must rotate together with Earth as Earth rotates about its own axis, the period of orbit for the satellite must be the same as that for Earth, 24 hours. Then we look at the direction of rotation of the satellite. To rotate together with Earth, its direction of rotation must follow the direction of Earth's rotation about its own axis, which is from west to east. And finally, this one might not be so easy to see, the plane of rotation of the satellite. Right? The plane of orbit of the satellite must be the same as the plane of the equator, which means that the satellite must be directly above the Earth's equator. It cannot be in the northern hemisphere or southern hemisphere. Right? The geostationary satellite must be positioned directly above the equator. Right? Let's look at why. So this is the equator, right? Based on what we've seen here, for satellite to be geostationary, it must move in this orbit. No other plane of orbit must be like this, from west to east, directly above the equator. Can a satellite at this position move in a geostationary orbit? Can it move this way? Right, it is not possible. Right, to move this way, you know that the net force, the centripetal force, must point towards the center of the circle, which is here. But at this position, the only force acting on the satellite is the gravitational force, which is directed towards the center of Earth. Right, Fg acts this way. So there is no way, right, the force can be towards the left this way. So at this position, right, if the satellite were to orbit, it will be orbiting in this plane. Okay? And if it is orbiting in this plane, clearly it cannot be geostationary because a person who is here will rotate this way, whereas this satellite rotates this way. The satellite will not appear to be directly above the person at all times. Okay? And that is only one plane for geostationary satellites, this plane, directly above the equator. All geostationary satellites have the same radius of orbit, right? Because just now we see in Kepler's third law, square of the period of orbit proportional to radius of orbit. Geostationary satellite, the period are all the same, 24 hours. So all of them must also have the same radius of orbit. So if you have 100 geostationary satellites, all of them must be found at the same height above Earth's surface because they must have the same radius of orbit. Right? They are useful because they allow a fixed antenna on Earth to maintain a constant line of communication with the satellite, because you can always, it's directly within your line of sight. Right? But this is not the only orbit that satellites can take. Right? We also have non-geostationary, or what we call asynchronous satellites, taking on other types of orbits. Okay, let's look at example 6. Right, you're given the radius of Earth and the mass of Earth. You need to determine the height of a geostationary satellite orbiting above the surface of Earth. Okay, so you're not finding the radius of orbit of the satellite. You're finding the height above the surface of Earth. It's a geostationary satellite. How do you start approaching this question? Orbiting bodies always think of the circular motion. Right, we always begin with summation Fr equals to MAC. Okay, but before you even write that equation, you got to write down that all-important statement. Right? What provides the required centripetal force? Okay, so here let me calculate what is the period of this satellite. Right? Geostationary satellite period must be 24 hours. You convert it to seconds. And this is the important statement you must write down before you write down the equation for circular motion. Right? You must identify the force that is providing the required centripetal force for the satellite to orbit. And then the circular motion equation, summation Fr equals to MAC. Right? Summation F, there's only one force, the gravitational force, gmm over r squared. ME is the mass of Earth. Small m is the mass of the satellite. AC, because I'm going to use the period, I will use mr omega squared rather than mv squared over r. I do not know the speed of the geostationary satellite, but I know its period must be 24 hours. And then omega, I convert to 2 pi over period. Right, and then I make r the subject of the equation because I want to find the radius of orbit. So when it comes to here, you just have to be careful not to make any careless mistake. The r here and the r at the denominator do not cancel. Right? It becomes r cubed. All done? Okay, then after that, you just sub in the values. But this is not the answer. You want the height above the surface of Earth, not the radius of orbit. So how are you going to find the height from here? You've got to subtract the radius of Earth, right? That will give you the height above Earth's surface. The radius of orbit, right, is the sum of the radius of the Earth plus the height of the satellite above the surface of Earth. So h is what the question is asking for. Okay, part B. How do you determine the speed of orbit? Do I need to go through the whole thing again? Summation Fr equals to mv squared over r. There is no need. Okay, once you know the radius of orbit, you know the angular velocity omega, you can find the linear speed v, right? Because it's a circular motion, v equals to r omega. All finished? Okay. So let's look at the phenomenon, right, of feeling weightlessness when somebody is in orbit in outer space. You've seen pictures, right, of astronauts in spaceships, right, and they all seem to be floating. Are they really weightless? Right, that's what we're going to look at now. So we have an astronaut inside a space vehicle orbiting about Earth. And this astronaut wants to weigh himself, so he stands on top of a weighing balance. Right, so astronaut inside the space vehicle, and here's the weighing balance. Now let's consider the three objects, the space vehicle, the weighing balance, and astronaut as one body. Right, so this body, this whole thing as one system, is orbiting around Earth. What provides the centripetal force for them to orbit? It's the gravitational force which Earth exerts on this whole system. Okay? So we say the gravitational force exerted by Earth on the space vehicle, astronaut, weighing balance system provides the required centripetal force for the system to orbit around Earth. Then the equation, summation Fr equals to mac. Mass here is the mass of the combined body, right, the whole system. And there's only one force, which is the gravitational force, equals to mac. Okay, and this gravitational force, I can write mg. Right, g is the gravitational field strength at this position out there in space. Okay, so the 2m will cancel. So the centripetal acceleration experienced by the system at this position, its numerical value is equal to the gravitational field strength at that position. Okay, and since g is gm over r squared, we can also write the acceleration as this form. Okay, so the centripetal acceleration at this position is no longer 9.81 because you are very far away from the surface of Earth. The value of this g will be much smaller, but it is not zero. Okay, so now, what this acceleration value means is that all the three bodies, whether the space vehicle, the astronaut, or the weighing balance, all three have the same acceleration equal to g, which is calculated by this expression. Now we're going to look at the free body diagram of just the astronaut. Okay, we look at the forces acting on the astronaut. There's the weight, the gravitational force that Earth exerts on him, and there is the normal contact force which the weighing scale exerts on him. Okay, we want to find out how much this weighing balance is going to show. Right, so because the astronaut is in circular motion, right, and he needs a force towards the center of the circle to provide the centripetal force. Looking at the two forces, the only force that can provide that centripetal force is the weight of the astronaut. Okay, so summation Fr is mass of the astronaut times the centripetal acceleration of the astronaut. On the left-hand side, there are two forces acting in that direction, right? We take the direction towards the center of the circle to be positive. So it's the weight minus the normal contact force exerted by the weighing scale. Right? So the sum of these two forces is the centripetal force. It must be equal to mg. We replace the centripetal acceleration with g. We've derived earlier, right, that the centripetal acceleration is equal to the gravitational field strength at that position. And this value of g will be much smaller than 9.81, but it is non-zero. And this gravitational force is mg. Right? The g must be the same, right? It's at the same position, so they share the same g. From here, we can see that the value of n is 0, meaning there is no contact between the astronaut and the weighing scale, so he appears to float. Okay? So the weighing scale shows 0, right? The astronaut feels weightless. He feels weightless because there is no supporting force acting on him, no force to support his weight. But is his weight 0? Clearly no, right? If his weight is 0, if this is 0, there's no way he can move in orbit. There's no force to provide the centripetal force. Okay? So he feels weightless because the weighing scale does not exert any outward force on him. So that's apparent weightlessness. But his true weight is not zero. Right? The weight is much smaller than the weight on Earth because the value of G is much smaller than 9.81. But it is not zero. Otherwise, there's no way he can orbit because you need the weight to provide the centripetal force. Okay, so that's the last page of your lecture notes. You'll see a comparison between G field and E field. Electric field is something you'll learn next year. It's very similar to E field, to G field. So you'll come back to this page after you have learned E field next year. Okay, it's not end of the lecture yet. What I'm going to talk about now is very important. Right, I mentioned before, right? Last lecture before block test is very important, so pay attention. But if you don't want to, lecture is over, right? What I'm going to say now is important, but if you don't want to hear, you can go off. Otherwise, please keep silent. Okay. If I give you this graph without the equation, it shows the KE of orbiting body, how it varies with distance away from the planet. Right? This R is also the radius of orbit. If I just give you this graph, there is no equation, all right? And then I ask you, right, does this graph show that EK and R are inversely proportional? How do you tell? You don't have an equation, you only have the data from the graph. How do you tell whether or not, right, EK, which is the y-axis, is inversely proportional to R? What must you do to check whether or not the two variables are inversely proportional to each other? Any suggestion? What does inverse proportion mean? It means that EK equals to a constant divided by R, right? That's inverse proportion. So if I want to show that it's inversely proportional, I must show that EK times R gives me a constant, right? So what I need to do is to pick any point on the graph, right? I pick this point, I take the value of EK and R at this point, I multiply them. How do I show it's a constant? Obviously, I must pick another point, right? And then I calculate EK times R. Is it enough to just take 2 points and the two product give me the same constant? I say yes, inversely proportional. Is it sufficient to just take 2 points? The answer is no. We need at least 3 points. Okay, so if you want to show that it is a constant, you must pick at least 3 points from the graph, find the product, and show that the 3 products are about the same. All 3 are constant before you conclude that EK and R are inversely proportional. But if I do 2 points and the product of the two values are already very different, do I need to go on to the third point? No need. If the 2 points already show that the product are very different, straight away you conclude that they are not inversely proportional. You don't have to go to a third point. A third point is only necessary if you want to prove inverse proportionality. Okay, next question. Now, it's the same graph, but this time, I give you the equation. Right? You know the value of G is in your data list. I give you the value of small m. The mass of the orbiting object, I give you the value. But I do not give you the value of big M. Big M is the body, the source mass, right? About which the satellite is orbiting. How do you determine the value of big M from the graph? Small m is known. How would you determine big M? Right, you can just pick any point on the line, on the graph. That point will give you the value of EK, give you the value of the corresponding R. You sub into the equation, you can calculate big M. But is that sufficient? I just pick 1 point and then I calculate big M. Is that sufficient? How many points do you need? What is the magic number? 3, as before, okay? So you pick 3 points. Each point gives you a value of big M. You find 3 values of big M from the graph. You find average big M. Okay, so everything that you read from the graph, you must have 3 points. Okay, so far we have always encountered linear graphs with linear scales. Some graphs, they may be drawn with logarithmic scale. Right, for example, if I have a value of x that range from 0 until 2 million, some values are 0.5, some values are 30, some values are in 100 million. How am I going to fit all those values within the graph paper? With a linear scale, you can't fit all these values. That's when we use a log scale. Right? This is what a log scale looks like. The intervals, the divisions are not equally spaced. Right? At the beginning, they're spaced further apart. Towards the end of the big square, they're spaced very close together. Same here, they're spaced further apart. Right? As you move to the right, they're spaced closer together. You need to know how to read a log scale. Okay, let's look at the first big square. It ranges from 0.1 to 1. So the first point here is 0.1. The next division is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Then you hit 1. The next big square is from 1 until 10. Right, this is 1. The next value is not 1.1. The next value here is 2. So you read it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the next big square is from 10 to 100. So from 10, the next division will be 20, 30, 40, 50, all the way to 100. From 100 to 1,000, it goes from 100, 200, 300, and so on. Okay, make sure you know how to read a log scale. Okay, just some things to note because some students have some queries on why is it that the way we calculate GPE is so different from what we used to do in WEP. So you need to know the difference. In WEP, we are more concerned about changes in GPE rather than the absolute GPE. Right? In WEP, we hardly ask you, what is the potential? We're always asking for change. What is the gain? What is the loss? Okay, so it doesn't matter what the absolute potential is at a particular point because you're only interested in the change. Also, in WEP, right, the objects, when they move, they're always assumed to be close to Earth's surface. And so we take G to be constant. And that is why the equation to find change in GPE is mg times the change in height. Right, because we take the small g here to be constant at 9.81. Right, so the questions you encounter in WEP, typically the distance involved, right, they are very close to Earth's surface. The g is assumed to be constant. That's why you can use this formula to calculate change in GPE. But in Gfield, this topic that we just discussed, we are talking about distance that are huge, right? You're talking about moving objects from one point to another point far away from Earth's surface. So the value of the gravitational field strength, small g, is no longer constant. Okay? And also in gravitational field, we learn how to calculate absolute GPE minus GMM over R. It is always negative, except at infinity, then the GPE is 0. Right? And because the G here, small g, is no longer constant, we cannot use this formula to calculate change in GPE in questions involving such huge distance from Earth's surface. Right? To calculate the change in GPE, we got to use this formula. Final GPE minus initial GPE. Okay, remember. So this kind of questions that you encounter in gravitational field, you can never ever use kinematics equation of motion to find acceleration. Because the force, the gravitational force, as you move across the distance, is not constant. The g varies, the gravitational force varies. The acceleration cannot be a constant. So you cannot use equations of motions to solve. The only concept you can use in Gfield question would be conservation of energy. Okay? And just another reminder, for this block test, Gfield is included, but it's only included in MCQ, not the structured questions. And the MCQs will not be very tough, right? We have pitched at a level such that as long as you understand all that we have taught you in the lecture notes, you understand the lecture notes example, you will be able to do very well for these few MCQs, okay? You won't find any questions on Gfield in your practice papers or your revision package because, as I said, the MCQs are fairly simple. As long as you understand that what is going on in the lecture, you will be able to do well. Okay. Yep, so I will end early today. Okay, you may go off.